Hello guys. So today we will be trying to solve this. So this is from the same paper TIFR 2025, and this is a true and false. So it's from part B, question six. Question six. So yeah. So basically it says that we have a sphere. I don't think I can draw a sphere here properly, but okay. Okay. Suppose we have a sphere, which is given by s square. So sorry. Now it's given that D basically is a restriction of the Euclidean metric. So basically we have the usual Euclidean metric on R cube and we have restricted it to the sphere. And it says that basically if F is a map, so we are given a map f a square to a square such that distance between fx comma fy is nothing but distance between x and y. So basically F is an isometry, right? So basically F is an isometry. So which and we know isometry. Okay, let me just read the question. So for all, so it's given for all x y belongs to. So basically it holds for the whole space. I mean, the whole sphere. So and it's given that f is surjective. So is it true or is it false? So we'll try to solve this. See that f is an isometry, and so in isometry it is injective. All right. Okay. Now, now basically we write. Let's say we have a sequence xn, like this of course belongs to s square, and it belongs to the sphere, right? So it converges to a point in x. Okay, so basically, we can say that so given the usual, given any epsilon greater than 0, there exists capital N which belongs to natural numbers, such that like d of xn comma x is less than epsilon for all greater in small and greater than capital N, right? Okay, so and now what is this? It's since it's isometry, the distance between xn and x is same as distance like between their images, right? So this will be distance between f of xn comma f of x is an epsilon for all n greater than equals to n. So, which implies that f of xn converges to fx when xn converges to x, which implies that f is continuous. F is continuous by sequential criteria. Okay, f is continuous by sequential criterion of continuity. Okay, now, so basically what we have that we have that f is continuous and injective. So this is a very important condition. Now, like how to approach the question. So basically, we have deduced so far that f is continuous and injective. Okay. Now, yeah. So now is f is surjective. So now let us talk about the structure of S square. Now S square is actually a two manifold, right? Because of course it's Hausdorff second countable and all that, and also, so let me go back to my very bad diagram. So and and locally, so you take this a neighborhood, so that will be homeomorphic to an open set of R square. I do take a neighborhood, so we can actually map it to R square, right? So basically this will be a two manifold. So we have a map from this to S square, which is all, I mean, yeah, which is a two manifold from S square to S square, such that F is such that F is uh, such that F is continuous and injective. So we can apply like the Brouwer's invariance of domain. So using invariance of domain, invariance of domain, using invariance of domain, we get f of s square is open in s square. Okay, f of s square is open by using invariance of domain. We get this point. Okay, so Brouwer's invariance of domain. So f square is open in S square. Now one thing is, since f is continuous and S square is it's closed and it's bounded. It's closed because you take any like point and you take an open ball, it will of course intersect. Right, okay, let me once again go back to our diagram. So if we take a point this and if we take any, open ball, which is also a sphere surrounding this, it will intersect the sphere. So yeah, so basically, so since it's closed, S square basically is compact, right? It's closed and bounded. Okay, so S square is compact. So since S square is compact and F is continuous, so basically f of S square will also be compact because if maps since it's in Rn and if so since f is continuous and it maps so basically maps compact set to compact set. Right. Now okay, so yeah, now since since S is now so yeah, so this is compact, so of course this belongs, so this is a subset of S square. Now since S square is compact and f of S square is compact in that, so basically basically it's a subspace of S square and it's compact, so basically it will mean that f of S square is closed. Right, so let me repeat this once again, that so basically f is continuous, f of S square, so continuous will map compact set to compact set. Since S square is compact, so f of S square will get mapped to, sorry, S square will get mapped to f of S square, and which is also compact since the whole space is compact. So this will be closed. Okay. So, but from our previous argument, f square is open, right? So now we notice that a square is path connected. Of course, it's path connected, right? So it will imply that this is connected. So in a connected, so in a connected matrix, so like a set which is both open and closed, and and also since f is injective, so it can possibly mean one thing. So it will mean that f of s square is nothing but s square. So this is f is surjective. So basically we got that f is bijective, right? So since S square, let me repeat this once again. Since S square is path connected, so it will imply it's connected. Now, f of S square, the image of f is basically both open and closed. Since it's a connected space, so a set which is both open and closed will be the whole space, right? Since of course f is injective. Okay, so yeah, so f is surjective. So this is true. It's our question. So we have solved this. This is true.